So it has been assumed that the elastic deformation is a time independent. When we apply stress, we will produce an instantaneous elastic strain that remain constant over time. And when we release the load, the strain immediately returns to zero, as we can see in the figure here. We can see in the figure that when we release the load, then well, we can see that the strain immediately returns to zero. However, for unelastic material, elastic deformation will continue after a stress application. So unelasticity, we can say it as a time-dependent elastic behavior. For metal, it is less, but in polymer, it is high. The term viscoelastic, we usually associated it with a polymeric material. For metal, we usually call it unelastic. So we can define viscoelasticity as the materials that exhibit both viscous and elastic characteristic when experience deformation. So how do we define viscous material? Before that, what is the definition of viscosity and viscous materials? Viscosity, we can define it as the measurement of a fluid resistant to flow. Examples of different materials that have a different viscosity are water and honey. For a viscous material, the strain will develop over a period of time, and after stress is removed, it does not return to its original shape. And the development of a strain takes time and not in phase with the applied stress. And the material will remain deformed when applied stress is removed. So we can say that in viscoelastic materials that is held under constant strain, if we wait, we can see that the level of stress will be decreasing over a period of time, and this phenomenon is known as a stress relaxation, as we can see here in figure A. On the other hand, recovery of strain refers to the change in shape of the materials after the stress that caused deformation is removed, as we can see here in figure B. And what are examples of viscoelastic materials? Some examples of viscoelastic materials include synthetic polymer, wood, and human tissue, as well as metals at a high temperature. And all these materials display quite a significant viscoelastic effect. So a common example of stress relaxation is provided by the nylon string in a tennis racket that we can see here. We know that the level of stress or the tension, as the tennis player call it, decrease with time. And what are the difference between a viscous material and viscoelastic material? Unlike a viscous material, when applied stress is removed, part of the strain will recover over a period of time. And the examples of a stress relaxation, as I mentioned before, is a nylon string in a racket. And for strain recovery, the example is when we put a heavy on a carpeted floor. So can you give me the definition of elastic deformation? Elastic deformation means that the material will return to its original position when the force is removed. And we can see that many metals in elastic region have a resulting strain that is proportional to the tensile load when applied tensile load is small, as we can see in the figure here. But during the elastic deformation, the bond, as we can see in this figure, we can see that the bond between the atoms are stretched or deformed, but when the load is released, the bond will go back to their original position. So we can see that elastic here means reversible. As we can see here, this is the examples of plastic deformation. For most metallic part, the elastic deformation is relatively small. At some point, the strain is no longer proportional to the applied stress. And at this point, the bond with the original atom neighbors start to break and reform with a new group of atoms, as we can see here. And when the stress that when this occurs and stress is relieved, we can see in the material it will no longer return to its original form. Means that the deformation is permanent and non-recoverable, and the material is now moved into a region that we refer to as a plastic deformation. and plastic here means a permanent deformation of that material. So here we have a two figure, and can you guess which one is a plastic deformation and which one is a elastic deformation? So we have a figure A and figure B. Figure A can be considered as a plastic deformation, and figure B can be considered as elastic deformation. So can you give me an example of materials that exhibit this type of deformation? Okay, this type of elastic deformation can be exhibited by a rubber type material. We can see that from the figure here, it does not follow the Hooke's law, right? But because we can't see a straight line, that proportional relationship between the force and the extension, as we can see for this figure, but we still consider this as elastic deformation. Hooke's law and elastic deformation is not necessarily the same thing. We can see that it does not follow the same path backward, right? And what does this mean? This means that more work is needed to stretch the rubber band compared to the work needed to unstretch the rubber band. And where does all the excess energy go? So all the excess energy is released as heat, and area under the loading, as we can see here in the figure, area under the loading is greater than the area under the unloading curve. So the energy loss is what we call as a hysteresis. Now we move on to the nonlinear stress strain curve within the elastic region. Both linear and nonlinear elastic materials will elastically return to an unloaded state after loading without a permanent deformation. But the relationship between the stress and strain is different in them. It's linear for a linear elastic material and more complex in a linear case. As we can see here, some materials do not exhibit linearity within the elastic region, and so it is not quite possible to determine the modulus easily. So as we can see in the figure here, it shows a stress strain diagram showing a non-linear elastic behavior. So how do we measure the Young modulus of this type of material? So before that, some examples of materials that do not exhibit linearity within the elastic region includes gray cast, iron, concrete, and many types of polymer. So how do we measure the Young modulus of this material? So this is quite an interesting category. I would include plastic and forms here as example. As if we recall from the previous lecture, steel, for example, has a small section just before yielding where it's not linearly elastic anymore. But this spot is so small that we can easily ignore it. The similar thing happened for this type of materials, but the zone is so big that you just can't ignore it. So we can say that for this type of materials, there is no linear plastic part. As we can see in the figure here, we can see it says that it is elastic zone but non-linear. What do you do? In this case, is quite simple. How do we determine the Young modulus of the materials if the elastic zone is non-linear? We can either assume that at the very beginning, the material stiffness is okay, and in such case, we will use a tangent. We will use a tangent stiffness. However, if you expect that this strain will be high, for example, it will be close to the start of the yielding, then the tangent stiffness is not very accurate. Instead, we can use a second stiffness. And this one is better for a higher strain but shows a too soft material behavior beforehand. So we can say that for second stiffness, the higher strain material with we can use it for higher strain materials with a too soft materials behavior, and for tangent stiffness, we can use it to determine the Young modulus as by assuming that at the very beginning of the materials, the stiffness is sufficient or okay.